Fellow chemists, here is some revision. This is what we went over in class the other day, video in case you need to come back and refer to it. All right, so first thing is pH is a measure of the concentration of hydronium in any solution. We calculate it by taking the negative log of the concentration of hydronium. The reason we do that is because the concentration of hydronium is usually quite a messy number, so we want to have it just be a little bit easier to write and to read. So you can rearrange that equation to find the concentration of hydronium from the pH. So if you know one, you know the other. Also, pH plus POH equals 14. So if you know pH, you can calculate POH and find the concentration of hydroxide from that. For example, if you want to calculate the pH of 0.001 mole per liter hydrochloric acid, you need to find the concentration of hydronium. In this case, it is 0.001 moles per liter, and then take the negative log of it. And that will give you the pH. We also use K and Q values. K values are a description of a reaction equilibrium, and Q values are a description of a reaction at any time. If your K value equals your Q value, then your reaction is equilibrium. If they do not equal, then it is not an equilibrium, and whether it's higher or lower can tell you a little bit about which one is which. See an earlier video for more info on that. Okay, the ionic product of water, Kw. This is a description of what is going on in pure water at 25 degrees C. Pure water at 25 degrees C has some hydronium and hydroxide in it. Not very much, but it does have some. It has 1 times 10 to the negative 7th moles per liter of hydronium, same amount of hydroxide. You multiply those together to find the Kw, so the Kw is 1 times 10 to the negative 14th. That is a constant. It will always be true for water. You can calculate the concentration of hydronium by rearranging Kw if you know the concentration of hydroxide, and vice versa. And the equation for doing that is for finding the pH. Once you know the concentration of hydronium is that. The acid dissociation content. This is one of our last K values. It is calculated the same way as any other K value with this equation right here. Since it is for acid, we call it a Ka, but you take the reactants, multiply the concentration by each other, put it over the products, sorry, other way around, products on top of reactants. And if Ka is small, that means that the conjugate base is strong. If it's very, very big, it means you're dealing with a strong acid. Sorry, a strong conjugate base. And since Ka values are often weird numbers, kind of like concentration of hydronium numbers, we take a pKa of them, which is the same thing as a pH, but it's of Ka. So we just do the negative log of Ka, and you can convert back and forth. pKa plus pKb equals 14. So if you know one, you know the other. Kb, which I just mentioned, is the same thing as Ka, but for a base. And Ka times Kb equals Kw. So if you look at the same equation we were looking, or kind of the same equation we were looking at before, but the other way around, you've got a base here, it's conjugate acid, water, and hydroxide. And we can get this equation here from that, which is the same as the Kb, or the Ka equation, but for this reaction here. And that is useful for us as well. Kb versus Ka, we've got Kb on top and Ka below. You can see how they are similar. Ka includes hydronium, Kb includes hydroxide. So, for example, we've got these two questions here. I'm going to go to the next page because that's where I've got my work. So, first thing we want to do for the first one is look at the, write out the equilibrium equation. NH3 plus H2O is in equilibrium with NH4 and OH minus. Write the Kw, and we are given a Kb, not a Ka. We want a Ka because we're asked to find hydronium or pH. So we rearrange that. Kb equals Kw of Ka. We know the Ka, so we can solve for Kb. Then we write the equilibrium expression for Kb. Gives us that number there. and then you make your assumptions that the concentration of NH4 plus is equal to the concentration of hydroxide, because for every one NH3, when it gains a hydrogen to become NH4, the water will have lost one hydrogen, so their concentration is equal, and the concentration of NH3 is equal to what we were given. Then we calculate the pH. We start with POH, because we can find the OH, so we calculate the OH, and we here, which we do by using the KB equation here. And then once we have the concentration of hydroxide, we can find the POH, which is this, and then we can calculate the pH by just subtracting it from 14. So pH is equal to that. And that is our answer. The other one I did on the board in class, it is very similar. So if we're looking at the last thing we need to know about acids and bases is that sometimes the products, the salts that are produced by an acid-base reaction are themselves acidic or basic, and that can have effects on the pH.